and welcome to Talk 3 for the City Room. If you're looking to find information about exploring the CERN open data using open software, if you're not here for that, you're in the wrong room. So you're all very welcome, and allow me to introduce Aman Desai. He's a PhD student at the University of Adelaide. He works on the Atlas experiment as well as the Future Circular Collider. Ooh, interesting. Is that the one that's going to blow us up? Okay, if you take your seats, and please give a warm welcome to Aman Desai.
Thank you. So in this talk, we'll discuss about exploring the CERN open data using open software. So, a brief introduction. CERN is the European Organization for Nuclear Research in Switzerland. By CERN open data, we mean the data which is collected by the Large Hadron Collider and made available to the general public for educational and research purposes. And for this particular talk, our focus will be on the Atlas experiment and the open data that has been collected by it. So what is this data about? We take two protons, collide them with 6.5 TeV energies, and this energy is equivalent to the energy of a flying mosquito. But this energy is squeezed into a very small region of space, and which is why this is highly impactful. And then we have a collision. Now, in this collision, we would have protons, photons, electrons, hadrons, muons, undetected particles, dark matter, anything. And all this data is going to be about these particles, and we'll discuss briefly about all of these in the coming slides. And just as an illustration, this is one of the typical events where a collision happens, and you have particles, you have a top quark, which is the heaviest quark produced, and then it leads to some other particles like jets and leptons, and as you can see, this is really complex. And this is just one collision, and we are analyzing billions of such collisions. And this is how it might look like in the real detector. Yeah. So in a single process, hundreds of particles are produced. This could include long-lived particles, stable particles, those like short-lived ones, electrons, photons, and each particles has their own properties. They have their physical properties such as their momentum, energy, their charge. All of this is collected and stored in data files by the collider. And every few years, CERN as well as the Atlas collaboration makes this new data files available to the public. And as well as they are also open source software, and we're going to discuss about that. This is the analysis chain. So you have a proton collision in the first picture. Is this working? Yeah. And then the detector collects this data. It feeds to the LHC computers. So we've got a large farm of computers, and then it goes on to physics analysis as a simple chain. And then we also need to simulate, because this is a really complex situation at the collider. So we need to simulate using computers, like Monte Carlo softwares, as to what we expect to happen. So physics and the world around us. So I'll just briefly tell you what all this is about. This is Adelaide, and this is the river. So you just magnify water, we get molecules of water, H2O. They are connected to each other. If we further magnify them, we have a water molecule, H2H and O. More magnification gives us protons, neutrons, as well as electrons. Now, what we are talking about here is subcomponents of protons and neutrons, which are called quarks, gluons. And this at such quantum level, and these particles that are moving with speeds close to the speed of light, and that is what we are going to study. Thus far, leptons that we talked about, the electrons and muons, they're considered as point-like objects. Of course, there are theories that they may not be so, but yeah, let's just, hold on to that. That is point-like. The length scales. The human hair width is 10 raised to minus 4 meter. Atomic physics, 10 raised to minus 10 meters. Nuclear physics, those that go in nuclear bombs, 10 raised to minus 15. We are working less than 10 raised to minus 17 meters. That is our scale at which we are working. And at these scales, we not only expect to find the fundamental physics that is going on in the universe, we also expect that there would be something new, something that we don't know so far in few hundred years of physics that might still be hiding there. And that is what we are trying. This is a picture. This is classical mechanics that is taught in schools, in colleges, first year, which is large objects, slow speeds, car for instance, or person walking. If one goes fast, let's say speeds that are in space, like really close to the speed of light, you have relativistic mechanics. That's where Einstein comes in the picture. If you go really small, that is quantum mechanics. And what we deal with is really small and really fast. So we need something called as quantum field theory to deal with that. And the all particle physics. Now, since some years, we have developed what is called as the standard model of particle physics, which is the framework that explains 3 of the 4 known interactions in the universe, namely the electromagnetic, the electrical shocks, for instance, weak interactions that go in nuclear decays, and strong interactions, we cannot experience them, but they undergo in those protons and gluons. It's strong and weak are some things that we do not directly experience. Electromagnetic, electrical shock, or if you just rub your skin, it's possible. Gravity is not explained within the standard model, which is one of the reasons that there's something that we still need to do to understand nature properly. The standard model, which consists of quantum states, and they are distinguished on the basis of properties such as their spin, all those kind of things. We're not going to go into that, but just to let you know that particles are differentiated on the basis of their properties, and will be down to just a few handful of particles that are actually fundamental. Again, time scales. Weak interactions are happening about 10 raised to minus 12 seconds. And I'm giving a talk for 45 minutes. So electromagnetic interaction, 10 raised to minus 18 seconds. So 1 second and divide that into 10 raised to 18. So 1, 0, 0, like 18 zeros, and that's just one electromagnetic interaction. And strong interaction, 10 raised to minus 23 seconds. So it's really fast. And this is what we have got after 50, 60 years of our studies in particle physics, which was followed up, with 200-300 years of physics. And what we are down to this: 6 quarks, 6 leptons, 4 gauge bosons, and scalar boson Higgs. The Higgs, I guess most of you must have heard about it, because of the 2012 Nobel Prize was given for this discovery. And this discovery was by the Atlas and CMS collaboration. These gauge bosons are the ones that actually mediate these forces. The electromagnetic interactions, for instance, you need a photon. A photon is also the light. So light is basically an electromagnetic wave. And then you have leptons and you have quarks. Quarks are fundamental constituents of the proton, some of them are not part of proton. And the leptons, electrons, we are all aware of. Muon is a heavier electron, and tau is the heaviest of all. Neutrinos, every moment as we speak, neutrinos are passing through our body, but we cannot feel that. It's because they are neutral, they are almost massless. But of course, it's not completely massless. There's some tiny, small mass, but we have not been able to find what. This is the LHC. It's 100-meter underground, so it's just a line at the moment. It's located right at the border of Switzerland and France. In fact, CERN is such that if you are in CERN, you might have to park your car in Switzerland and have lunch in France. So, and that's where we have got 4 experiments. Atlas, which is there. Oh, sorry, is right here. Then we've got LHCb, which deals with flavor stuff like the different quarks. The CMS is just like Atlas, but the smaller version. And then we have got Alice, which is heavy ion stuff. We won't discuss in detail about these LHCb and Alice or CMS, because I come from Atlas, so I'll just discuss about that. But questions are welcome on any of those colliders experiment. This ring, this circular particle collider, is about 27 kilometers circumference. And the future circular collider that was mentioned that I work on is going to be 90 kilometers at the same place. At the moment, LHC is the world's largest particle collider. And it collides protons with this 13.6 TeV energy. Just as an illustration, 1 TeV is just the energy of a flying mosquito, and then you multiply it with 13. The only thing is that you squeeze the energy in such a small space that it's more than what you could produce a lot of particles with that. Just imagine 2 flying mosquitoes colliding with each other, and then the fragments of that mosquitoes, and one can analyze that. These are the different experiments that are happening. This is just the pictures of that. I'll not go into the details of experimental details. That's not essential. But what is essential for our open data is that the way we collect data is we divide it into periods of run periods. So different runs have associated different energies. So run 1 was 7 TeV, 8 TeV, which was used for the Higgs discovery. So it was important. It got the Nobel Prize. Then in run 2, the energy was increased. It was almost twice the run 1 energy. There was more physics that could be studied, more Higgs physics, as well as new searches for particles. At the moment, the collider is running. And the collision energy is 13.6 TeV, which is highest ever. And then in this particular run, the number of collisions were increased, and we'll see how many. And then run 4 is going to be extremely high. It will be in late 2020s. And it is going to be extremely high rate of collisions per unit area per second. Yes. So when these 2 protons, they collide, this leads to this kind of a picture. So that is what the detector records. And at LHC, every 25 nanoseconds, we collide 100 billion protons. That's the rate at which we do. So it's 25 nanoseconds and 100 billion protons colliding against each other. Just very high. Even then, only 50 protons or 50 could actually be, seen by the detector, or they would actually collide, because protons are very small in space. So what happens is, at the end, we don't have many, but still it's it's important to see that there are 100 billions every 25 nanoseconds. The ATLAS experiment, it's a toroidal Large Hadron Collider apparatus. It's cylindrical in shape with a length of 46 meters and a diameter of 25 meters. It weighs 7,000 tons and has 3,000 kilometers of cables. By size, you can imagine that this is a 5-story building with all devices and cables running from one place to the other. And this is the detector itself, and this is some people who are working, and this is the size to scale. This is the people who are working in there. This is a... And then there are 4 such detectors. So yeah, it's enormous. It's 100 meter underground, yes, so it's fine, it's safe. ATLAS detector is designed, of course, to measure particles' momentum, energy, the trajectories where they are flying, and then other characteristics. For example, we need to know the charge of the particle, like is it positively charged, negatively charged. It consists of subcomponents because you need to have different components to measure energies, to measure the charge, measure trajectories. Then we have specific, for muons, we have different things. We have got magnets to bend the charged particles. That's how the detector is made up of. This is a picture, illustration of how these particles would actually travel. So we've got a photon, electron, muons, and as you see, muons have the furthest track. If you got an electron, it has a straight line, but as it enters this orange box, there's a shower. The same thing happens for protons. There's a shower in the orange box and an even bigger shower there in the calorimeter. It's because the way this detector system is designed to... yeah. So identifying the physics objects. So this is one of the primary tasks, and by physics objects we mean electron, photon, and muons, and how they are detected and how they are stored. I'll skip these details for the moment. And this is also because different particles, we've got dark matter which leaves the detector itself. So these objects that leave the detector, as you will see an example of one of these things later on, is called missing transverse momentum. So these particles basically leave the detector. Even if they exist, they leave. And the only way to find out is that they leave something missing, some missing component, and that is the missing transverse momentum. We'll discuss this, and there's also a tutorial later on in the afternoon, and where there might be some more details on this. This is a collaboration. We are 6,000 members from 42 countries, 182 institutions. If you go through the list of countries, there will also be countries which are not politically good with each other, but they work very well in our group. And it's 42. The map is a bit old. It's 1 month old, and now we have 42 countries. Yeah. The aim of the open data is to provide data and tools to the public, and then also to increase, the idea is to increase physics analysis, awareness, the focus being on education, training, and outreach. Between 2014, 2016, ATLAS released about 8 TV data sets collected during 2012. This was actually very useful because it was used for many educational master classes, as well as in Kaggle. Kaggle had a competition as well in 2014 using this data set to discover the Higgs. In 2020, ATLAS released another fraction of a data set from 13 TV, and recently, July 24, 65 terabytes of data was made available. In total, CERN has provided about 5 petabytes of data. So we discussed this machine, and then this open data is also used by, not just for educational purpose, but also by researchers who use this for reanalysis, reinterpretation, making more theory, developing theories, algorithms, machine learning, everything. It allows, so yeah, yeah. And it also inspires future generations, of course. The open data is stored available in various file formats. These file formats were developed by CERN, for CERN in the beginning, so they were developed back in 2000s. But now they are being made available for astrophysics, as people in astronomy also use some of these root files for their studies. This is just evolution from the 8 TV release to 13 TV, and we've got 10 times more data now, which is public. This is the website, which has got tutorials on that website. You can play with the interactive tools there. There's also how to do some research with high quality data, which is recorded by Atlas. So there are several types of data, which could be for research, education. So we also got high quality research data. This is one of the Atlas websites, the CERN website, where you can actually go and download anything, any of those samples. And as I said, CERN has released about 5 petabytes for public. So it's quite enormous. This is one of the websites where once we do an analysis, CERN and Atlas requires us that we we submit our figures and our data to this website as well. So this website will have all the data that is used in plots in our papers. It's kind of, we usually submit it there on this particular portal, and anyone can access it. It's an open website. Some of the open source softwares. So Monte Carlo simulation is, as a technique to calculate probabilities. It plays an important role in corroborating experimental results as well as in designing future experiments. The chain is such that we generate some events. So by event, it means we simulate some of the proton-proton collisions. Then we send these collisions for detector simulation, where we simulate the Atlas detector, and then finally we reconstruct physics signals. And there are all of these softwares that we use are open source. They're available for anyone to use anytime. And they're free. All of these is free. Yeah. So this websites, this softwares like MadGraph or Pythia are commonly used, and in fact they are quite easy to use for beginners. Most beginners in our field start with MadGraph because it's really simple. And then this Pythia is basically some kind of specialized software that allows you to generate showers of particles that we saw in the previous picture. These are the websites to MadGraph. As you can see, they've also followed some Ubuntu-like numbering. So there's one long-term stable release, and then there are short-term releases, which are 3.5.x, and then 2.9 point something is long-term. This is JET. The idea here is, as we saw the shower of particles, it's basically, we don't call it shower of particles, we just name it JET. And it's important that these kind of things are simulated properly in order that we don't miss out our new physics signal. Event generation by Pythia, so that is what is done. So this JET are basically one of the things that Pythia does. Then detector simulation, which is very important because we've got this 5-story building, and we need to know what each component, the 5-story building, which is like the detector, and then we need to know what each component is actually responding to that particular signal, physics. So that's how these tools were developed, are being used, and all of this, it's like, yeah, it's open source. Anyone can use it. They've got their own documentations to work with. For example, Giant 4, and they've got their own get started. Anybody can get started with this. Download their documentations. There are also open source, there are also forums where you can post questions, and mostly these are very active forums, so you can get answers very quickly, but 9 hours behind. It's Europe, so it follows Europe time, so yeah. Then this is Delphi's fast simulation. So this is a tool which is detect a response and is faster, the idea here is that if you want to do a quick study of physics, people start with this, and if you want a more detailed study, you go with Giant. Then for reconstruction, the idea is you've got this detector signals, and then you need to find out or infer what physics is going on. In that case, there are reconstruction softwares. Atlas has its own reconstruction software, which is called Athena. And there's a tutorial later on where you'll be using, indirectly you'll be using the Athena software within Jupyter Notebooks, but that would be very indirect. And this, since December 2018, this was made public, and it's mainly written in C++, Python, and there are also lots of examples. For the collaboration itself, there are also tutorials conducted. This is the GitLab page. It's not the actual, it's gitlab.cern.ch, and then it's Athena. I'm sure it should be open, and yeah. And as you can see, there are about 143,000 commits so far, and 2,500 forks. Yeah. Our project, our Athena software is divided into multiple components where we do different types of things like simulation, event generation, so it's just all divided orthogonal to each other, so yeah. CERN root is one of the well-known software. You'll be using this software in the tutorial. Most people in the field, they use root software. In fact, root is also being used by astrophysicists nowadays. This is the website. Again, it's open source, and it was used to analyze petabytes of data scientifically. One of the important things about this software is the software installation environment. In order to make this easy, there are also some virtual machine file system which has got all those softwares installed. All you need to do is just install this virtual machine. I have a picture. Oh, sorry, I missed it. So there's also there's a link, so you can probably just Atlas virtual machine, and you can get all of that on your own computer. For educational purposes, one can also use the open data Jupyter notebooks, which we will be using. Physics with open source, so a lot of physics studies can be done, but since we are short of time, we'll just discuss on Higgs a little bit. So Higgs was discovered in 2012. It fulfills the validity of the standard model, and it plays an important role for responsible for masses of particles. And it has a mass of about 125 GeV, which is 200,000 times heavier than the electron. So it's very heavy. Being heavier than most standard model particles, it can decay into those particles. These are some of the decay modes. So it's basically probabilities, the way Higgs would decay. And in the tutorial, we'll be discussing about the gamma-gamma, which is not here because it's really small, but it's a very clean channel. This is example of a data set. It's a condensed thing, so we have several columns there. We store our, whatever is necessary to analyze physics, like momentum, whether it's a lepton, its trajectories and information on that. And this is one of the columns, so it's just numerical data. This is missing energy, by the way. These are some of the plots. This is from so on the right, this plot is from the open data, and on the left, this is the actual discovery plot that was used in the paper. And as you can see, that there's this bump, this small bump in both cases. And that small tiny bump led to the discovery. Among other things, there were also other channels that were used. This is how one can read, but I'll skip this. This is also another channel where this, as you can see, there's this particular blue column, and then this data is a bit shifted. So all of that led to the fact that there's something new in that region, and then after thorough research, they found out that, yeah, this could be the Higgs. And we are going to rediscover the Higgs today in our tutorial. The use of artificial machine learning in particle physics dates back to 1990s. That's when the first time they were used. There was boosted decision trees that were used back then. And nowadays they use anomaly detection, graph neural networks, boosted decision tree, deep learning, and many other things. And the main goal is to identify what is the signal, let's say Higgs, and then to distinguish this from all the background that we know. And this was the Kaggle competition. It was back in 2014, and it's still available. Anyone can still have their own notebooks and run them. Later this afternoon, we have a tutorial, so please join us. And in this, as a summary, in this talk, we explored some of the features of the Atlas open data and open source softwares. We also explored aspects of physics involved in collider experiment, and and then we have a tutorial hands-on session, and then we thank the Adelaide Atlas group for discussions, and these are some of the references and books, and that's all. Thank you.
Thank you very much.
Happy to take questions.
Okay, see if we can make this work. What do I do, audio people? Push. Is it on? That's not on. Anyone for questions? Questions?
I can just try and project, I guess, if the mic isn't working.
I have to get the speaker to repeat the question for the audio stream recording.
Yes. So is this working? Are you hearing it?
No. Can I have a look? If we could just get the speaker to repeat the question, I think.
Alright, so I know in quantum mechanics, it's really important when you measure something, right? Like collapse the wave function and it behaves in a more classical way. So I'm curious, at what point in the collision are you measuring things and like collapsing the wave functions? Is it after the protons have hit each other and sent off all the little particles?
Yeah, it is after that.
Can you repeat the question so they can hear it on the system?
So it's about when do we actually measure. So as he shared in quantum mechanics, the wave function would collapse at the time you measure something. So the question was whether we measure this before the when they collide, or when these fragments fly away. So yeah, it's after the fragments actually fly, and then that's recorded in the detector.
What is the purpose of releasing the data? Is it for citizen science, or is it more just for educational use?
He wants to know, is the data being released for citizen science or is it just educational? Is that right?
It's for educational purposes. It's also used in schools in year 11, 12. It can be used at undergraduate level, graduate level. It is also used for research, some of that data. So the purpose is like multi-purpose, yes. And there are different levels of data. Depends on, so the data that we use for educational purposes is as simplified as possible. Then you can have the next level data, which could be used by theorists. If one goes further, in the next level would be raw data directly from the detector, the signals itself. And yeah, so there are different levels of data. The data for machine learning would be different, yeah. Yeah.
So does CERN have all the software it needs now, or does it need to develop more?
Research always, yeah, it's going on. So So the question was whether CERN has all the software or is it developing, is it in the process? So it's always in the process of developing more, but we have got our own softwares, yes. So for analysis, we have got our own CERN root framework. It's also possible to do machine learning within this framework, although at the same time, we also use PyTorch and other softwares, yeah.
Any more questions? Now, there's just a reminder that you've got the tutorial, the tutorial will be in City Room number 3 at what time?
3:45.
At 3:45 to go and explore this much more than what we've given you in this introduction to. So I would like you all to please thank Aman again for his very interesting I would like to this is just a token of our appreciation for you giving your time and energy and helping everyone. These are made by one of our volunteers on the core Everything Open team, and it's pretty nice. We'd like to thank you.
Oh, thank you.
Thank you very much.